Hello and welcome back to Dr. Logic Awkwardly Does Logic, unfortunately without any cats this time. Now that you've gotten all of the rules of replacement and all of the derived rules and everything, I'm going to give you a quick example just so you can see how to put a bunch of these things together. It's going to be an example that shows that from the fact that you have a false conditional, so not P implies Q, you can get a conjunction of the truth of the antecedent and the falsity of the consequent. So I will do this using the derived rules, including the rules of replacement. And then if we have space, I might try to sketch a proof of what it would look like without these rules so that you can see just how much work we're actually saving ourselves. So up comes the whiteboard, make it full screen. And again, let's hope that Zoom record things properly. So what I'm going to show you is that if you have not P implies Q, from this you can derive P and not Q. So we've got one assumption, and that is the negation of the conditional. I've got a stray negation, the bane of a logician. They pop in where they aren't wanted, they disappear where they are wanted. They're never any good. Anyway, there's our initial assumption. So now we want to prove this conjunction. Our proof strategy says, assume the negation of the conjunction. Assume the negation of what you are trying to prove, and then eventually use negation elimination. So we've got not P and not Q. Now, if we had, this is an assumption for negation elimination. Now, if we just started with this and then tried to use all of our basic rules, we'd be like, what do we do now? We have two formulas whose main connective is a negation, and none of our rules allow us to do anything with that. And so you would have to do a whole bunch of very complicated, more assumptions and other bits and bobs and things. But since we have our rules of replacement, we can look at this one. It's a negated conjunction. So right away, you can apply De Morgan's to it to get not P or not Q. So that's one of the instances of De Morgan's applied to line 2. So we're trying to get some sort of contradiction from our assumption of not P and not Q. The only thing that we have right now that we could contradict with is line 1, this negation of P and Q. So what would happen if we were actually able to prove P implies Q? Then we could reiterate line 1 and we'd get our contradiction. So let's see if we can prove P implies Q. So I'm going to make a new assumption, and I'm going to add myself a note that I want to get Q. Well, double negation allows us to put two negations onto any formula or subformula that we want. Now here, I'm applying it directly to line 4, so I'm applying it to the entire formula. I mean, P is an atom. It doesn't have any subformulas other than itself. But once I've got not P, well, this is the negation of not P. Not P is one of our disjuncts in this disjunction. This means that if either not P or not Q is true and not P is true, so it's not the one on the left, it has to be the one on the right. This is disjunctive syllogism using lines 3 and 5. But negations are a pain. You saw it earlier. So if you can ever get rid of them, let's do that. So going from not Q to just Q, applying double negation to line 6. But look at that. Q was what we wanted to get. So conditional introduction says that if we have P, then we can get Q. And this is justified with the subproof at lines 4 to 7. But the reason we wanted to get P implies Q is because it is the negation of our first premise, which says actually it's not the case that P implies Q. So if we reiterate line 1, we have a contradiction, and negation elimination allows us to get P and not Q from the subproof lines 2 to 9. So as I said, if I were going to try to do this without using the derived rules, I would get to this point where I've got my first two assumptions, and then I would need to do something in order to be able to get something that doesn't have negation as its main connective. Now, the fact that you can go from 2 to 3 using the De Morgan's laws indicates that there has to be a way that you could have gotten this without using that rule, just using some of the basic rules. So you might say, well, I'm going to try to say not P or not Q. I'm going to assume this, except here again, we've got something else with a negation in the front. So we haven't really gotten any further into anything that would be useful. How about if I say, golly, at this point, I know I'm going to do the assumption of P. So suppose that we assume P, then if we assume not Q, so you can see we're already nested like 5 subproofs in, and this is going to get complicated. But suppose I assume not Q, then I would be able to get P and not Q through conditional introduction, lines 4 and 5. But then this gets me, I can bring down this conjunction from this negated conjunction on line 2 through reiteration. So now I have P and not Q, and also not P and not Q. So this means I can get rid of that negation right here through negation elimination. My assumption of not Q led me to a contradiction in lines 5 to 7. So let's go with that. Apologies for the sound of the kettle boiling in the background. We're almost done. So from our assumption at line 4, we were able to get line 9, we were able to get Q at line 8, which means at line 9, we can introduce our P implies Q here. So conditional introduction, lines 4 to 8. Oh, look, okay, this isn't going to turn out too much more complicated than the other one, but certainly it wasn't immediately obvious to me when I got started how I was going to actually finish. But here we've got our conclusion. Now we can go over to here. Oops, not 3, 11. This is line 11. We can get here not P or not Q through negation elimination, lines 3 through 10. And now you can see we have gotten at line 11 where we are here at line 3. So a number of these other steps, disjunctive syllogism, double negation, are probably going to have similar blowups. So if I were to complete this proof, it would probably end up being about 50 lines. Maybe there's a more efficient way of doing it with, again, with just the basic rules, none of the derived ones, but who wants to spend the time figuring it out? So there's an example of something that is much, much simpler with the derived rules. And I don't know about you, but now I want a cup of tea. So take care, enjoy your tea break, and see you later. Cheers.